Good afternoon, everyone. I am delighted to present our work, Acoustic Model Fusion for End-to-End Speech Recognition. In this study, we've explored advanced techniques to push the boundaries of speech recognition, aiming to solve some of the field's most challenging problems through innovative acoustic model fusion. Let's start by discussing the evolution of speech recognition. Over the years, we've seen a shift from traditional systems to sophisticated end-to-end E2E models. These E2E systems, powered by deep neural networks, have simplified the speech recognition pipeline, but challenges remain, especially in adapting to diverse speech patterns and domain-specific jargon. The E2E systems implicitly model all ASR components. AM, LM, and lexicon are implicitly learned in a single neural network in E2E ASR systems, so the internal AM performs inadequately on long-tail words and phrases as their constituent. Word pieces are rarely seen in the training data. Moreover, the internal pronunciation lexicon does not well capture the pronunciations of rare or unusually spelled words. Fusing a separate LM trained exclusively on text corpora into the E2E system is beneficial. However, LM fusion presents certain drawbacks, such as its inability to address the domain mismatch inherent to the internal AM. We propose the integration of an external AM into the E2E system to better address the mismatch. We have achieved significant word error rate reduction, up to 14.3% relatively, across varied test sets. We also discovered that this AM fusion is particularly beneficial in named entity recognition. Our methodology involves a two-step process. First, the E2E system generates initial hypotheses. Then, we employ a second-pass rescoring using an external acoustic model. This external model brings its strengths to bear, re-evaluating the initial hypotheses and significantly reducing error rates. We conducted extensive experiments across various datasets. These included speech from virtual assistants, dictation scenarios, and synthesized speech samples containing named entities. This diversity allowed us to rigorously test our model under different conditions. We first apply AM fusion on top of conformer word piece without LM using conformer monophone. At the first glance, the improvement is not as significant as LM fusion. However, this is expected because LM is fused in the first pass such that it helps expand the search space, and AM is fused in the second pass, which is limited by the N-best quality. The N-best qualities can be indicated by the Oracle word error rate of the systems. We then apply AM fusion on top of LM fusion. The relative improvement using conformer monophone is similar to AM fusion in the non-LM setup. Word error rate reduction is larger on TTS and voice assistant than on dictation, which shows that AM fusion helps undertrained words and named entities. We then conduct AM fusion with SNDC-NN Triphone. As SNDC-NN Triphone is a more powerful AM than conformer monophone, leading to a significantly greater AM fusion word error rate reduction, especially when LM fusion is also employed. Despite this, conformer monophone is still of great interest, because it uses the same front layers as conformer word piece, so we can eventually combine it with conformer word piece through layer sharing and multitask training. By doing so, we can potentially achieve decent AM fusion improvement with little inference cost. We next try to understand how AM fusion affects rare word recognition. We train a word piece N-gram LM on the E2E training data. We divide each dataset into 5 buckets of equal size based on word piece PPL. Infrequent words fall into the high PPL bucket with larger chance. We can see that on voice assistant than on dictation, as PPL increases, higher word error rate reduction is achieved, which confirms the effectiveness of AM fusion in improving underrepresented word pieces. As we purposely inject named entities into every TTS utterance, the PPL difference between buckets is tiny, which explains why the TTS curve is flat. We examine the effectiveness of AM fusion on LibreSpeech in a similar way. In these experiments, we only use conformer monophone as the representative of the phoneme-based models. Additionally, to make a fair comparison between LM fusion and AM fusion, we build a new baseline where LM is used for second-pass rescoring. We can see that AM fusion provides more improvement than LM fusion when they operate on the same search space, no matter whether the base system is fused with LM or not. In domain, AM fusion brings consistent improvement. We next take conformer monophone from the previous experiment. There exists clear domain mismatch between the AMs. We fuse the out-of-domain phoneme-based model with the E2E ASR model with or without LM. Because the AMs are not acoustically consistent, the out-of-domain conformer monophone contributes less improvement than the in-domain conformer monophone. Though the out-of-domain conformer monophone has huge mismatch, the gain from out-of-domain conformer monophone AM fusion is still significant, indicating that a large amount of improvement might come from the external knowledge injected by the explicit lexicon. As conclusion in this work, we proposed AM Fusion, which integrates an external AM into the E2E system via second pass rescoring. An AM score is computed for each first pass hypothesis in the N-best list for re-ranking. While second pass AM Fusion brings significant improvement, it is limited by the first pass accuracy. Hybrid systems can work well on unusually spelled words, such as foreign names, but those words might not even appear in the N-best list output by the E2E system in the first pass. Therefore, first pass AM Fusion is appealing and can potentially help the recognition substantially. Our next milestone will be streaming AM Fusion in the first pass.